Hello, welcome to our next discussion. And our discussion here is regarding rocks. And in this particular chapter today, it encompasses a lot of material regarding both the three rock groups: igneous rocks, sedimentary rocks, and metamorphic rocks. In fact, one can actually study several semesters in an undergraduate degree program and get a bachelor's degree in geology, and you spend most of your time looking at the processes and identifications of these major three rock groups. Your earth science book happens to try and take, or at least most earth science books, try and take all three rocks groups: igneous, sedimentary, metamorphic, and put it into one chapter. So that makes way for a lot of vocabulary. It makes way for a lot of discussion on how you differentiate the identification between each one of the rock groups. And so what I tried to do in this chapter, of course, is just narrow it down to what I think is important for the level of earth science. So that means as we go through this discussion on rocks, I think you should make sure you take some note paper and make some clear, definite notes as we move through the different rock groups, and make sure that any vocabulary that we talk about and mention, that you certainly write those vocabulary words down, and of course master the content meaning of each one of the vocabulary words. So again, what we're going to do today in this discussion is talk about igneous, sedimentary, and metamorphic rocks. And really what's important here is if you look at the bottom of your screen, it says keepers of earth history. And in fact, that's very true, because rocks tell the story. As we kind of move through the content material with these three rock groups, you'll find that geologists certainly can use the rocks. And since geologists understand where the rocks came from and how they're formed and the processes behind the formation of each one of the rocks, it kind of tells you the story or the origin, if you will, on how our earth came about, the history. And in fact, I like to look at rocks as pages of a book. And if you can read the rocks, allow the rocks to tell you what they're telling you, you can certainly find a lot of information about your earth. Okay, so let's start off with what's in your rock. And of course, that comes from that famous commercial, "What's in your wallet?" Well, in this case, what's in your rock? Remember, we talked about earlier with minerals that we said elements make minerals and minerals make rocks. So if we start with minerals, for example, and we'll start with this very common mineral called hornblende. And we add to that hornblende some orthoclase, which is another very, very common surface earth mineral. And we add quartz to this makeup. So now we have hornblende, orthoclase, and quartz, which are some of the most common rock-forming minerals on the Earth's surface. We certainly can produce the rock granite. And so typically a true granite is a type of igneous rock in which it has a large proportion or percentage of quartz. And if you look at this picture, you can kind of look and see some of this pink area, which would represent the orthoclase mineral. And then some of the hornblende would be identified, represented by some of the black specks in here. And there's probably another mineral in there called biotite that we could also add in there. The key term here in terms of what's in your rock and describing a rock is the term aggregates. And aggregates is a type of term or word that just means groups. And so, again, we look at rocks, and if the person identifying the rock, the geologist looking at the rock, understands the composition of the rock, for example, then again, that tells the story of where that rock comes from. So we can say by definition that a rock can be aggregates or groupings of various mineral assemblages, but also a rock can be whatever the earth wants it to be in terms of how the earth processes material on earth. And so, for example, a rock can be composed of biological material. So here you have a rock that has pieces of shells and shell fragments and so forth. Here we have a rock that can be composed of fossil fragments. So again, a rock can be anything the earth wants it to be. And then here we have a rock composed of plant material. So as we go through looking at the igneous, sedimentary, and metamorphic rocks, you'll see that these processes then will dictate the type of rock that is produced, and it's the geologist's job to take a look at that rock and what's in that rock, and again, tell the story. So what's in your rock? Again, aggregates of minerals, but it can be biological, fossil, and plant materials, and whatever the earth wants it to be. Like maybe we can look at an example where if we could hang around the earth for, I don't know, another 5,000 years, there might be a new type of rock that comes out that comes from ancient human dump sites. And that material has been cemented together, and who knows, maybe they'll come up with a different type of rock composed of our human debris. Okay, so again, in any geological degree, understanding rocks and what rocks are and how they form is a basic foundation of knowledge for any earth science or geologist. So as I kind of alluded to at the beginning of the discussion, every rock speaks to the observer and gives clues about where and how it was formed. And so we can divide rocks basically into three major rock groups. And most of you have probably had some introduction earth science course somewhere in your educational endeavors. And you probably have come across igneous, sedimentary, and metamorphic. And so in this particular slide, what I'd like you to be able to do is I would like you to be able to make sure that you can come up with a one-sentence brief statement that describes each one of the rock groups. Then as we go through this discussion, we'll expand on that. So you could be walking down the street someday and somebody hits you on the shoulder and says, "What's an igneous rock?" And then as an educated person, you certainly can make that one brief statement. So we look at igneous rocks. Igneous rocks are formed from solidifying hot molten magma, meaning that if we take hot liquid rock, which is about 2,000 degrees Fahrenheit, we allow that rock or that magma, in this case, to cool. And as that magma cools down and it becomes totally solidified, we now have a certain kind of igneous rock. And so really, an igneous rock represents frozen magma. Sedimentary rock forms on the surface of the earth, and it forms through weathering processes. And so we'll touch a little bit on that in this chapter, and we'll talk about how a sedimentary rock forms, and then the next chapter will actually talk about weather processing or weather processes more in detail. So for our brief statement then, sedimentary rocks are formed on the surface of the earth from weathering processes. Metamorphic rocks are rocks that have been subjected to pressures and temperatures. So when we say pre-existing rocks, we're saying that these are rocks that are before pressure and temperature. So they could be an igneous, sedimentary, or even another metamorphic rock. But these are rocks that are subjected to pressure and temperature. So your goal at this point should be to come up with a brief statement that describes each one of the rock groups. In fact, this would be a good point for you to stop the video, write down the brief statements for each one of the rocks, and then continue with the statement when that's done. Okay, so how does an earth scientist then distinguish between the three rock types? So every semester as I teach geology and I teach earth science courses, inevitably I will have students come in and say, "Professor Pierce, what kind of rock is this?" And then based on my training and experience that I've had over the years to be a geologist, I will implement two major criteria that just comes right to me when I look at the rock to be able to put it in some kind of identification category. The first thing we look at is texture. And texture basically represents the appearance of the rock. And when we say appearance of the rock, we're talking about, we look at the individual grains that make up that texture, and we look at the size, the shape of the grains, how the arrangement of the mineral grains are in the particular rock. And again, based on that texture, that tells you the story in terms of where that rock came from. So we have learned in the past that when we use this word texture, most students and folks want to say that texture is how the rock feels. All right, does it feel rough or smooth and so forth? You can get away with that because what makes it feel smooth and rough is the size, shape, and arrangement of the grains. But that's not what we're looking at in the geology world. We're not looking at how it feels. And in fact, if somebody says to me that this rock, if someone says, "How does this rock feel?" Sometimes I will say, "Well, is it sad or is it happy?" So we want to stay away from that definition with respect to how it feels. But instead, we're going to look at the size, shape, and arrangement of the mineral grains. The next criteria we look at is composition of the rock. And when we say composition, we're looking at mineral assemblages or types of minerals that make up the rocks. And what's important to a geologist is the relative proportion of the minerals. In other words, the percentages of various minerals and so forth. Composition can mean mineral makeup, chemistry. They're all indicators of rock composition. So again, as a geologist, when someone brings in a rock, again, my training first looks at the texture, and then I look at the composition, and together with texture and composition, geologists are able to classify and put that rock into its particular category. Is it igneous? Is it sedimentary? Or is it metamorphic? In past semesters, I would take students out to the San Andreas Fault Carrizo Plain area, and I'd have like 60 to 80 students at a time, and we would look at rocks and so forth. And inevitably, again, I would have a whole bunch of students bring me rocks during the field trip, and they would say, "What's this? What's that? What's that?" So again, I would go back to texture composition. But one time I got kind of exhausted at looking at rocks, believe it or not, and a student brings one up and says, "What kind of rock is this?" And I said, "This is leverite. Leave it right there." All rocks are identified based on their texture and composition. So make sure you master the definition and concept of what we mean by texture and composition. So this next slide now takes us into a type of cycle known as the rock cycle. And what's it mean to be a cycle? Well, to be a cycle kind of means that there's really no beginning or there's no end. And if you look at this rock cycle, you can typically go to the internet and you can type in the rock cycle and look under Google Images, and it would show you, 10,462 different types of graph that illustrates the rock cycle. So this particular rock cycle basically looks how one rock can merge and turn into another rock through different types of processes. By convention, because there really is no beginning or end to this rock cycle, but by convention, it's always good to start with magma, because we'll find out a little bit later that most geologists most regard magma as the parent rock or the beginning of all rocks, which is probably some truth to that. So we look at magma, and we find out that magma can either cool below the Earth's surface or above the Earth's surface. In any event, cooling magma is going to produce igneous rocks. Now, if those igneous rocks are subjected to the surface of the Earth or on the surface of the Earth and subjected to weathering processes, meaning wind, water, ice, and erosional processes, then those rocks will chemically and physically change, and now we become a sedimentary type rock. So again, there's our weathering processes. And so as it becomes a sedimentary rock, one can then, this right here represents the sedimentary cycle. And within these sedimentary rocks, there is the cycle of weathering, transportation, deposition, and sediment. Later on in the discussion, we'll get a little bit more detailed with respect to the sedimentary cycle. But now we can take this sedimentary rock and through various processes allow this sedimentary rock to be buried. And as the sedimentary rock gets buried beneath some depth on Earth, and then heat and pressure is applied to that pre-existing rock, and then that pre-existing rock becomes metamorphic rock. Now, nature can apply pressures and temperatures to the point where that metamorphic rock begins to melt, begins to turn back into magma, and then we can start the rock cycle process all over. Now, another interesting aspect to this rock cycle is what we did is we covered the entire cycle. But if you look at some arrows inside the cycle, those little arrows represent what I like to call sub-arrows, meaning that the rock cycle doesn't always have to follow igneous, sedimentary, and then metamorphic rocks, but instead you can take an igneous rock, for example, and you can metamorphose it, so you can bypass sedimentary rocks. Or you can take a metamorphic rock and you can re-metamorphose another metamorphic rock, and so forth. So the point here is that, yes, it's a cycle. There's no ending or beginning to the cycle, but there's also sub-arrows in here. And the rock cycle is pretty unique because it's a very, very slow, continuous set of processes that create the igneous and sedimentary metamorphic rocks. And a typical human life of about 80 years, we don't really get to see the immediate effects. But if we were allowed to, be on Earth for 1,000,000 years, we would see the effects of the rock cycle. So it's a very slow, continuing process of cycling. So if we kind of look at the rock cycle with a little more depth, we can kind of look at the rock cycle and compare it to what I like to say Earth's internal forces meets Earth's external forces. And really what's happening is the battle, if you will, between internal and external forces really produces the rock cycle that we see today. So for example, internal forces, if you come down here on the slide, may represent moving continents, earthquakes, elevation of mountains, which is a result of moving continents, volcanic eruptions. So these represent these internal forces. And while these internal forces are taking place, at the same time, we have Earth's external forces acting on internal forces. So some external forces could be the hydrosphere, which is the water processes that take place on Earth, the atmosphere, which have some water processes in there. There's erosion, wind, water, and ice, and maybe some biosphere activity. So again, while the internal forces are basically creating rocks and mountains and so forth, the Earth's external forces are basically taking the mountains down. So it really is I would like to say a tug-of-war process. While the Earth is making mountains, then the external forces are tearing the mountains down. So really, if you come down to the very bottom part of the slide, with internal forces acting with external forces, and I'll just kind of read the bottom of the slide because I wrote this myself. It says, produces a continuous cycle of rising mountains only to be weathered down and uplifted repeatedly. As a result of this battle, if you will, between forces, igneous, sedimentary, and metamorphic rocks are created. And so really, that kind of typifies what the rock cycle represents. And I remember a long time ago in the theater, I was watching a movie called The Time Machine, and I believe it was written by H.G. Wells. And I think there's two versions out there. There's the older version of The Time Machine and the newer version. I personally like the older version. But in this Time Machine, if you ever watched it, there was a scene where the scientist who made the time machine was starting to travel through time. I believe he was injured or something, and he fell against this lever in his time machine, and he advanced the time machine, I think it was about 1,000,000 years into time, into the future, and it was within, 30 seconds. But what was really neat is in the background of this movie, the special effects, is they showed mountains rising, mountains falling. They showed, I think, a glacier coming over, advancing. The glacier receded. They showed rivers. And basically what they were showing was a sped up version of the rock cycle that we don't get to see in our lifetime. And so, of course, I was the only one in the theater to stand up and just say, all right, the rock cycle, and clap my hands and so forth. So if you ever get a chance, maybe you can go on your YouTube and look up The Time Machine, and that scene is on there. You can see if you can find that scene, and you'll get a really good depiction of what the time or what the rock cycle really represents. Because again, we don't really see it in a human's lifetime. We see evidence of it, but we don't see it directly. So let's now follow the rock cycle. So as we kind of talk about the next three rock groups, igneous, sedimentary, and metamorphic rocks, we're going to kind of go through and follow the rock cycle. So again, the ideal place to start, of course, is with magma, and then we'll talk a little bit about igneous rocks, and then we'll move into sedimentary, and then we'll conclude the discussion using metamorphic rocks. So this first slide now introduces igneous rocks. I like this slide. It's a slide from Hawaiian Islands. And what I like about this slide is you can see a mixture of solid igneous rock along with lava in this case that is beginning to solidify and make the igneous rock. This particular type of lava flow in Hawaii is called pahoehoe lava flow. It appears to be that way from what I can see, meaning it's a very ropey, high viscous type lava. The other type is called a'a. So when we get into volcanoes, we'll talk more about that. So to start with magma, so I should say mag, and then the ma, A should be up there. So in magma then, magma is either going to cool below the Earth's surface or above the Earth's surface. And as it cools either above or below, it's going to produce two distinctive types of igneous rocks. If magma is allowed to cool above the Earth's surface, those are known as extrusive igneous rocks. And these are igneous rocks that have cooled very fast, sometimes termed as volcanic rocks. And typically, and this is very important in the geology world, and that is if magma cools above the Earth's surface, it's no longer termed or regarded as magma, but instead it's termed as lava. So let me repeat that. If magma is above the surface, it has now become lava. So if you ever want to make a geologist squinch, just say, look at the magma coming out of that volcano, and then they'll kind of be like rubbing fingernails across a chalkboard. So we're going to use the term lava. So in this case, then we would say that extrusive rocks are solidified from lava flows. Probably the classic example that we can bring out here is the Hawaiian Islands. So if you've been to Hawaii and walking along the beaches of Hawaii and so forth, you're walking on predominantly extrusive type igneous rocks that have cooled above the surface. So if we have lava cooling above the surface, then conversely, we can have magma that now solidifies or cools below the surface, and we regard those rocks as what we call intrusive igneous rocks. And so these are rocks that have cooled below the surface, intrusive. A term is used to describe intrusive rocks as plutonic rocks. Plutons, I believe, is a Greek word for below. So plutonic rocks is another term. These types of intrusions or intrusive rocks are responsible for the large granitic mountains that are observed, especially on the western part of the United States. One of the largest granitic mountains that we have is just east of us. That would be the Sierra Nevada mountain range. And so you should be asking yourself a question, and that is if the granitic mountains, for example, the Sierra Nevada mountain range, has solidified or formed below the Earth's surface, why can we see it today? Why is it above the Earth's surface? And that will be a topic that we'll mention and talk about when we get to plate tectonics. So extrusive igneous rocks cooled fast above the Earth's surface. Intrusive igneous rocks cooled slow below the Earth's surface. If we talk a little bit about magma, if you go back up to the top of the screen, magma represents the parent material for all rocks. Typical temperature is about 2,200 degrees Fahrenheit. Magma will typically form about 250 kilometers, or if you look at the top of your screen, 150 miles below the Earth's surface. That's where pressures and temperatures are such that solid rock can begin to melt. I knew a colleague or had a friend who was working on his doctorate degree at the University of Idaho when I was attending, and he was a volcanologist, meaning he was a person that studied volcanic rocks. And so his PhD dissertation was over at the Galapagos Islands, which is a set of islands just off the coast of South America. And one of his duties, or one of his research duties, if you will, was to take samples of lava. And so I asked him, I said, wow, I mean, how do you do that at 2,200 degrees Fahrenheit? And he says, typically they take a very long pole with a sample cup that doesn't melt, and they can dip it in the lava. But he was indicating to me that even if you're 15 to 20 feet away from a lava flow, the heat is so intense that's radiating from the lava flow that it literally singes the hair and the eyebrows on your body. So sounds like hazardous work there. Okay, so again, going back to how can you tell the difference between an intrusive igneous rock versus an extrusive igneous rock? So in this class, you will learn the basics behind identifying, basic characteristics of rocks. And so when we look at the igneous rocks in this class, hopefully when you get out, you'll be able to distinguish if this rock was extrusive or was an intrusive type igneous rock. And what's going to determine that is if you look at the bottom of your screen, it's going to be grain size. And so we're primarily going to focus on texture of the igneous rock to give rise to the classification. And then we'll focus a little bit on composition. So the next slide then presents two igneous type rocks. One igneous rock is a extrusive igneous rock, and the other one is an intrusive igneous rock. And so again, by looking at grain size, we should be able to determine which rock is formed above the Earth's surface, which rock or which magma solidified below the Earth's surface. And so if you look at the rock picture on your left-hand side of your screen, this is regarded as an extrusive texture. And this means that this particular lava cooled above the Earth's surface. So now think about this. If you got 2,000 degree lava extruding from a volcano, and as that 2,000 degree lava comes in contact with, let's say, 75 degree air, is this lava going to have a tendency to cool fast or cool slow? And the answer in this case is it's going to cool very fast. So typically the lavas will cool very fast. And as the lava cools fast, the atoms really don't have enough time to set up and come together to form visible mineral grains. It kind of goes back to our last discussion in minerals when we asked the question, what three conditions must exist for beautiful mineral crystals to form? And we decided it was time, solution, and space. And so when we look at the extrusive texture, lots of space, lots of solution, but lacks the time. So it cooled very fast. So because it cooled fast, it's going to create a type of igneous rock texture that we refer to as fine-grained, meaning that the mineral grains are there, but you cannot see them unless you use some type of instrument like an optical microscope or something that your eye cannot see. So these are mineral grains that are not seen by an unaided eye. So I'm going to give you a buzz geology word that describes a fine-grained extrusive type igneous rock texture. And if you look at my arrow, this word is aphanitic. So we would say that a extrusive igneous rock has an aphanitic texture, right? So put that vocabulary word into your vocabulary dictionary, aphanitic. If you look at the rock texture on the right side of your screen, this is a typical intrusive texture. So it cooled below the Earth's surface. And so in this case, if it cooled below the Earth's surface, it had a lot of time to cool. So it cooled very slowly. It had a lot of solution. So there was definitely enough materials to make the rock. But guess what? In this case, it lacks the space. And so you're not going to get these nice, beautiful crystal faces that we talked about in the last mineral discussion, but instead you'll see parts of mineral faces. And so we would say that these are visible mineral grains. And when we say visible, meaning that you can see them without using any kind of magnifying glass. An unaided eye is like what folks like to use. And so this is a coarse-grained texture. And the geologic term we use to describe a coarse-grained intrusive igneous rock texture, we use the word phaneritic. Okay, so a phaneritic is coarse-grained, aphanitic is fine-grained. So right now, if a person brings you an igneous rock, you should, at this point, just looking at texture, tell that person that this rock is either formed above the Earth's surface or formed below the Earth's surface, just by the fact that you can see the grains or you can't see the grains. So let's shift our gears now, because we looked at texture and common texture. And so let's kind of now look at composition of igneous rocks, because we're going to put both texture and composition together here in a second, and then we're going to classify 6 common igneous rocks. So when we look at composition, we're looking at how much silica is in your rock. And why would we choose silica and oxygen, for example? What did you learn about silica and oxygen in the minerals discussion? Is that silica and oxygen are the most dominant elements found on the Earth's surface. So given silica and oxygen then, and most igneous rocks contain some concentration of silica and oxygen, we can use that now to determine the composition. So for example, if we have an igneous rock with a composition that has, for example, 70% or more SiO2 or silica in the rock, typically that's going to produce an igneous rock that is very light colored. A light colored igneous rock, 70% or more silica. We refer to this as if you look up here on your screen, a felsic composition. So a felsic composition represents high silica type rock. And typically what kind of minerals you're going to find in a felsic composition is a group of minerals called feldspar and certainly quartz. So feldspar and quartz are going to make that rock very light colored. So if you have a light colored composition, what would be the opposite of that? And that would be a dark colored type igneous rock. So if it's colored a dark color, then that's indicating that you are at least 50% or less silica. Okay, so in this case, the silica has dramatically decreased. And what takes the place is iron and magnesium. And so the rock now then, if it's dark colored, is heavier or more concentrated in magnesium and iron. And so we use the term mafic to describe a rock concentrated in iron and magnesium with less silica. Ultramafic compositions, if you come down to the bottom of your screen, ultramafic compositions really is very, very high in iron and magnesium, and really composed entirely of 2 minerals called olivine and pyroxene, and definitely has less than 50% silica. So when you pick up an igneous rock, if it's light colored, guess what? It'd be felsic composition. This is how easy we're going to make it for earth science. If we pick up a dark colored igneous rock, then it's going to be in a mafic composition. But the earth isn't really separated with light and dark rocks. There are colors, if you will, in between that. And we refer to that as an intermediate compositions. And this is basically represents a mixture, an equal mixture of felsic and mafic minerals. In fact, there's one particular rock we'll talk about in a minute that's known as what they call the salt and pepper rock, which has a 50-50 mafic and felsic. So we've looked at the 2 common textures of igneous rocks, and that would be the phaneritic and aphanitic textures. We've kind of now looked at a color grouping of the igneous rocks, which represents composition, either felsic, mafic, or intermediate. And now what we're going to do is put those 2 characteristics together, texture and composition, and we're going to create a chart in which we can now identify the 6 most common igneous rocks. This next slide shows you Mount Rushmore, which from the picture looks it's an igneous rock. It looks very light colored. We'd say it's felsic. We would look at the texture. It's very phaneritic. And so given a phaneritic texture with a very felsic composition, Mount Rushmore is actually intrusive, meaning that these were granites that solidified below the Earth's surface. So we're going to classify now the igneous rocks, again, based on texture and composition. And we're going to classify them using what I like to call an X and Y axis, or a little grid here. Again, if you look at the Y-axis, we're going to plot texture along the Y-axis. So here you have coarse phaneritic, and then below that is fine-grained aphanitic texture. And then along the X-axis, we're going to plot composition, and then where the X-axis and Y-axis converge or cross, that is going to be our rock type. So let's start on the composition side of the classification chart. Let's start with felsic, light-colored, 70% or more silica. And if we look at the phaneritic texture with a felsic composition, we get the rock granite, which happens to be the most common continental rock on Earth, granite. And then if we look at the aphanitic texture of a felsic composition, we now look at the volcanic rock that we call rhyolite. We come to the other end member of the compositional part of the diagram. Then we look at mafic, dark colored, 50% or less silica. And then we look at a phaneritic texture that's very mafic. We call that the gabbro. And then we look at the aphanitic texture, very mafic composition. We regard that as basalt. And basalt is the most common volcanic rock on Earth. In fact, if you are visiting Hawaii, we said earlier that those are all volcanic rocks. You're mostly walking on basalts. In fact, I think some folks have mentioned to me that they liked, when they visited Hawaii, walking along what I think they call it the black beaches of Hawaii. And really, you're looking at sand-sized grains, but there's really sand-sized basalt, and that's where that comes from. If you look at the intermediate color, so this would be, again, 60% silica, 50-50 light and dark. We look at the diorite, which is the phaneritic, the coarse grain texture. This is the salt and pepper rock that we mentioned earlier. If you kind of look at the picture, you kind of get that idea between salt and pepper, light and dark. And then the andesite represents the volcanic rock, that's the intermediate color. So it's your job for the exam to learn the common 6 igneous rock types. And there's a couple ways to do this. One can just learn granite, diorite, gabbro, rhyolite, andesite, basalt, and then try and learn 6. But I actually find better that the mind works better if you just learn 3 things. So in this case, you learn 3 pairs. So for example, let's go to granite and rhyolite. And you look at granite and rhyolite, what's the same about granite and rhyolite, and what's different about granite and rhyolite? And what you find is granite and rhyolite are compositionally the same, aren't they? They're very felsic. Both rocks have the same minerals, but texturally they differ, because granite formed below the Earth's surface, rhyolite formed above the Earth's surface. So really what we would say then is granite is the chemical equivalent to rhyolite, or vice versa. Compositionally equivalent. Compositionally equivalent. On the other hand, we can go over here to gabbro and we'd say basalt is compositionally the same as gabbro. We'd say andesite is compositionally the same as diorite. So instead of learning all 6 rock types, learn the pairs: granite rhyolite, diorite andesite, and gabbro basalt. And so you can bet on the next exam that you have in this class, you will be asked about the chemical equivalencies of each one of these rock types. And you'll have to be able to identify which ones are phaneritic and aphanitic versus their composition of felsic and mafic. So igneous rocks have the same chemistry, but different textural characteristics. And right there, that textural characteristics tell you and indicate to you that that's the environment that particular igneous rock formed in.